Hello and welcome to WinXAS Tutorials, where I want to talk about the very important atomic absorption correction to obtain the EXAFS chi of k function. As always, the WinXAS software and the XAS data I will be using in the hands-on session can be obtained from the WinXAS website. The atomic absorption correction, or mu0 fitting, is the next data reduction step after background correction and normalization. Mu0 fitting can be regarded as the most important step in data reduction because it strongly influences the results and the validity of the following EXAFS analysis. For example, the range of the chi of k determines resolution and number of independent parameters in the EXAFS refinement. Spectral features that are removed by a poor mu0 fitting may invalidate structural parameters obtained from EXAFS data analysis even without being noticeable. Therefore, the atomic absorption correction should be performed as carefully as possible, and it may come as no surprise that various procedures exist to do so. I want to briefly introduce them here and then show their effect on the resulting EXAFS chi of k in the hands-on session. Prior to the atomic absorption correction, the x-axis of the XAS spectrum needs to be converted from the energy space to the k-space. This requires determining the E0 value of the sample spectrum, and the procedures used for this are the same as those used for energy calibration. The particular feature in the spectrum used for E0 is again less important than always using the same feature in your data reduction. For example, if you want to compare spectra with and without a pre-edge peak, it may be better to use the first or second maximum after the edge from the first derivative than using the inflection point from the second derivative. However, this needs to be decided on a case-by-case basis. Atomic absorption refers to the evolution of absorption as a function of photon energy for an isolated atom without any neighbors and thus without modulation of the absorption coefficient. For calculating the EXAFS chi of k, the atomic absorption is commonly approximated by a so-called spline function that is refined to the experimental spectrum in the EXAFS region. This refinement can be performed in either the K or the R space. K space refers to the regular spectrum, while R space refers to the Fourier transform space. For the refinement in R space, the chi of k is calculated using the current spline function and subsequently Fourier transformed. Minimized in the refinement now is the total signal in the low R range as given by the delta R parameter. This assumes that no nearest neighbors should be present at these low interatomic distances, and thus amplitude of the Fourier transform should be close to zero. Additionally, performing the refinement in R space permits using the Nyquist theorem to estimate the number of independent parameters and use it as the number of spline nodes for the atomic absorption. Both options can be selected or deselected during the mu0 refinement. Performing the mu0 refinement in the R space and minimizing the total signal in the low R range will be suitable for the majority of samples. However, for compounds with very short nearest neighbor distances, like, for instance, certain molybdenum or vanadium oxides, the underlying assumption may not hold true anymore. In these cases, It may be beneficial to perform the refinement in k-space while using a combination of spline function and theoretical WinXAS function based on a suitable model structure. An example for this approach will be shown in another tutorial. Coming next is the hands-on session. Objectives will be the atomic absorption correction using various procedures and Fourier transformation of the resulting chi of k function. The WinXAS spectra I will be using are included in the raw data folder of the tutorials data folder, which can be obtained from the WinXAS website. Given the importance of the atomic absorption correction, I encourage you to spend some time with the corresponding procedures and get a feeling for the effect of the various parameters. Let's get started and open an experimental data file. Again, this will be copper cluster 3. With all the settings in place, we can just calculate the absorption spectrum. So what we want to talk about today is the atomic absorption correction and Fourier transformation. In order to speed up this video a little bit, I want to use the quick WinXAS option here, and just for background correction and normalization, and then work on this spectrum. This is just for the purpose of this tutorial, and of course you should not do that when analyzing your own data. So this is the absorption spectrum of the sample in photon energy, and as I mentioned before, in order to calculate the atomic absorption and from that the WinXAS chi of k, we need to convert the energy range into the k space. For that we need to calculate an energy threshold of the spectrum, very similar to what we did for energy calibration, and that then will be used to convert energy into the wave number. So the menu here, the item is set E0. That correlates to calculating the either threshold for the spectrum. We did this for the energy calibration, and now for the spectrum. It's the very same procedure using the very same dialog here. And again, the program automatically searched for the maximum in the first derivative and calculated the first inflection point. So if you want to use this for the conversion, then that's fine. For the purpose of this video, I will select another feature. Let's go for this first maximum here in the experimental spectrum. So going to select a range that includes the root of the first derivative. I will search for this root in this range and take this value now as energy threshold to calculate the k space, to convert the spectrum from energy into k. So click on OK, conversion into k space, OK. And now this is our converted spectrum absorption as a function of k. And this now we can use for the atomic absorption correction. Again, XAFs, and this is called mu0 fit here. And we want to use the first option, which is the cubic spline fit. Alternative procedures here I may cover in another tutorial. The cubic spline fit, the number of splines and the k way to choose. We just take the pre-selected value here, and this opens this dialog box that I already showed in the first part. So now what we need to do is select the range for the atomic absorption that should exclude the xanes. So let's start with the left border here and just
perform the refinement to get an idea of what the results look like. So this is always what you will see at this step. This is the experimental spectrum. The red trace is the experimental spectrum, absorption as a function of k. And the green line here is the spline that will serve as the atomic absorption when calculating the XAFS chi of k, which is displayed down here again at a red trace. The blue curve here is the first derivative of the atomic absorption spline, and it basically serves the purpose of recognizing oscillations in this spline that may actually subtract significant data from the experimental spectrum, which of course you do not want. Well, from this XAFS chi of k, then, by the means of Fourier transformation, the radial distribution function, or the pseudo-radial distribution function, is calculated, and this is displayed here in the top right corner. So what are the options now? Well, the options are to change the number of splines, of spline nodes, and to change the fitting procedure from K space to R space, and change the left and right border. Let's start with the right border here, and this is where this button comes in, the step fit. This allows you to stepwise decrease or increase this value. There's no increase in this case because it already includes the entire spectrum, but we can decrease this, and with every click here, this is calculated. Again, the spline is calculated, the chi of k, and this Fourier transformed, and both the previous and the current radial distribution function are displayed here in red and in blue. So the blue trace is the previous radial distribution function, and the red trace now is what you obtain when you Fourier transform the down here displayed XAFS chi of k. This is for comparison. This is to see what effect changing this border actually has on the radial distribution function. And ideally, the effect should be small. Well, it should only be a small effect showing a stable atomic absorption correction refinement. And this is definitely the case here. So, we can do the same with the left border, increase this and see how this affects the XAFS chi of k and the radial distribution function. And again, you see there is very little change to the radial distribution function when changing the left or the right border. So this is a quite stable atomic absorption correction. The autospline, I explained that this calculates based on the Nyquist theorem the number of independent parameters and sets those as spline nodes. If you want to use more nodes, then you actually have to switch that off. And then you can go to parameters and change the number of spline nodes in the refinement. For instance, increase this to 9. If you want to, click on OK, perform the refinement again. And you see red and blue trace, and again, little change by this increase of the number of spline nodes. This will, of course, change when you significantly increase this number of nodes. Let's say we go to 15, do the refinement again, and then you see there is too much flexibility, definitely too much flexibility now in your spline function. It starts to follow the oscillation in the absorption signal, and this is, of course, what you do not want in your refinement. So we go back to autospline. This will set the value back to the number of independent spline nodes as calculated from the Nyquist theorem. And so this then gives more reasonably looking atomic absorption, XAFS chi of k, and radial or pseudo-radial distribution function. The R-space button here changes between K-space and R-space. Obviously now the refinement is performed in the R-space, so it is minimizing the total signal in this range here from 0 to 0.9 in on this scale. And so you see there is little signal in this area anyway, but this is also or this also depends on the sample, of course, because this is copper metal, this is small copper metal clusters, but the nearest neighbors are all copper atoms at an higher distance. So here in this case, the effect of performing the refinement in the K space or in the R space is actually very small. Again, this is a very stable atomic absorption correction here for copper metal. So having said this now several times, apparently here for this tutorial, this example just serves to introduce the general procedure. It is not so well suited to show the potential problems and potential pitfalls of the atomic absorption correction. But don't worry, I will be covering this with a different spectrum, a different sample in another tutorial. So let's say we're satisfied by the atomic absorption correction, we're satisfied with the XAFS chi of k, then we can just OK and close this dialog, and this will then result in the XAFS chi of k function that can now be saved, first of all, and then used for subsequent data reduction and data analysis. So XAFS refinement, basically simulation, and really to try to extract structural parameters. Normally, XAFS simulation and refinement is being performed in the R space. So the next step is Fourier transformation, and we briefly want to have a look at this. So in the XAFS menu, you find Fourier transformation. This will open a dialog box that gives you options. So first option is the window function. You can select different window functions like a Bessel window or a Hanning window. What are those windows function? Well, let's look at no window. That basically applies no window, and the XAFS chi of k as is will be Fourier transformed. If we choose a Bessel window, for instance, show window, you can see the blue curve now. This is the window function, and this will be multiplied to the experimental data, resulting in the green trace, and the green trace then is what is going to be Fourier transformed. So this basically reduces the amplitude, the left and the right of your spectrum, and this will result in significantly less side wiggles left and right from your main signals in the pseudo-radial distribution function, and we will show an example of this in a few seconds. The next thing is a Hanning window. For instance, here you see it also reduces the amplitude, left border and right border, but significantly less than the Bessel window does. So this will also reduce the side wiggles from your main signals in the radial distribution function, but way less so than the Bessel window. The Bessel and the Hanning window are the most used windows, I would say, in X-ray absorption spectroscopy data analysis. And it comes down to personal preference again, what window you prefer for your own data analysis. And again, you just have to use the same window all the time if you want to compare radial distribution functions from different samples. So you cannot compare Bessel transformed chi of k with a Henning transform calculator. That's not going to work. But if you're always using the same window function, then you can compare the two. Let's briefly have a look at the chi of k. What effect does that have on the Fourier transform? So if we select the Bessel window here, you can actually look at the differently weighted, so this is k1, k2, and k3 weighted chi of k being transformed using the Bessel window, and this is what you get. This is a chi of k, a k3 weighted Fourier transform. And you see there's a maybe reduced resolution, but also reduced side wiggles here to the left and right of the main signal in the radial distribution function, compared to, for instance, using no window. And you can see the signals are narrower, but there is more left and right, more of those side wiggles, if you want, from the finite range that you are using for the Fourier transform. So again, down to personal preference, I will use the Bessel window now and also in the following tutorials for the Fourier transformation, and then we can select this and this. Okay, and so now we're getting our pseudo-radial distribution function. It's called a pseudo-radial distribution function because the distances you see here do not correspond to the crystallographic distances. So the distances in copper and metal, for instance, and also in those small copper clusters should be about 2.5 angstrom, and so this is shifted to smaller distances, normally by a value of about 0.4 angstrom. Going back to the chi of k here, if you want to calculate a corrected Fourier transform where the distances actually corresponds to the crystallographic distances, this can be done. This is then being called a phase and amplitude corrected Fourier transform. In order to calculate that, you need either experimental phases and amplitudes or theoretical phases and amplitude. And this is the way to do this. I am not going to show this now, maybe in a future tutorial, but you can read about this in the manual, of course. So just going back, showing the radial distribution function now, what we see here, and there is a button here where you can actually toggle the display of the real and the imaginary part of the Fourier transform. So this is the Fourier transform of the WinXAS chi of k. It consists of a real and imaginary part. The pseudo-radial distribution function is the magnitude of this Fourier transform. So it's basically the square root of real part square plus imaginary part square. And normally the combination of the two, so the magnitude and the real and imaginary part, are being used then later in data analysis, so in WinXAS simulation and WinXAS refinement. Okay, so this is Fourier transformation. This is the atomic absorption correction to obtain the WinXAS chi of k, and using Fourier transformation then to obtain the radial distribution function, which normally ends the data reduction and marks the beginning of data analysis. So WinXAS simulation, WinXAS refinement, trying to extract structural parameters from those WinXAS measurements. Okay, that's it for this tutorial on atomic absorption correction, and I look forward to seeing you in the next one.